Welcome to the deep dive. Today, our mission is really to get past the noise and focus on some critical insights from really cutting-edge medical research. We're diving into the evolution of cancer treatment. It's this field that, well, for a long time felt defined by this idea of collateral damage. For decades, chemotherapy was the main weapon. Essential, yes, but kind of a blunt instrument, wasn't it? It killed fast-dividing cells, which meant inevitably hitting healthy tissues right alongside the cancer cells. Patients faced immense toxicity. The fight often felt like battling the treatment as much as the disease.
Absolutely. That was an era focused on, let's say, generalized poison. But then, starting in the late 90s, early 2000s, a huge shift began, a conceptual one. Researchers stopped seeing just a lump to be, blasted or cut out. They started seeing this complex collection of cells using specific, identifiable molecular pathways.
Yeah.
And that change allowed us to move from those broad toxic treatments towards highly specific, targeted molecular strategies, a real revolution.
That perfectly sets the stage. So we're going to walk you through, let's say, the three main pillars of this revolution. We'll explore how scientists are now fighting cancer by almost recruiting the body's own systems, not just poisoning invaders. But first, let's anchor ourselves quickly in those traditional methods and then see how targeted therapy was that first big leap. So if you look at conventional treatment, particularly for something like colorectal cancer, which worryingly we're seeing more in younger people.
That's a concerning trend.
The foundation is still early detection, right? Colonoscopy, looking for polyps.
Crucial.
Surgery can be curative if it's caught early enough. Radiation offers a fast way to knock back a tumor locally. And chemo, well, that's been the mainstay for ages.
Right. But the big insight, really over the last couple of decades, was moving beyond just treating what you could see. Targeted therapy means finding the smoking gun.
The specific trigger.
Exactly. The specific genetic thing, or maybe a protein signature, that the cancer is actually exploiting to grow. So, for instance, if we spot a mutation, like an epidermal growth factor EGF mutation, we don't use the blunderbuss of chemotherapy anymore. We use a homing missile, an EGF inhibitor designed just for that target.
That comparison, blunt force versus homing missile, that really clarifies targeted therapy, disrupting one specific pathway.
Yes, exactly. The inhibitor drug is chemically built to block that mutated protein signal. It essentially turns off the cancer cell's go switch for multiplying. And this approach generally means better results with fewer side effects because the drug is primarily designed to interact only with that mechanism the tumor relies on.
Okay. So let's unpack the next big strategy that came out of this targeted thinking, this idea of cancer-starving treatments, anti-angiogenesis.
Right. This research really changed how we view tumor growth.
Yeah.
Angiogenesis, that's the process where tumors basically trick the body into building them their own infrastructure.
Like laying down roads and pipes?
Pretty much.
Yeah.
Their own blood supply to feed themselves. And what's fascinating is that tumors have a strict size limit if they don't get this supply line. Without those blood vessels, a microscopic cancer just can't grow beyond maybe 2 or 3 millimeters in diameter.
Tiny, like the tip of a ballpoint pen.
Exactly that size. At that point, they effectively starve. They become dormant because they can't get enough oxygen or nutrients. Physics traps them.
That's such a critical point, and contrast that tiny controlled size with what happens if the cancer does manage to flip that switch, get its blood supply going. The sources we looked at detail these experiments. It's incredible. Allowing blood vessels to feed one of those tiny microscopic cancers can make it grow. Get this, 16,000 times its size in just 2 weeks.
It's explosive growth.
Just fueled entirely by those new supply lines, blood vessels gone wild.
And the research pinpointed the trigger for that growth. It's a molecular signal called vascular endothelial growth factor, VEGF. Tumors pump out VEGF to tell the body, hey, we need blood vessels over here. So once researchers understood that mechanism, they could develop drugs to block the VEGF signal.
And that block became the first anti-angiogenic drug, approved by the FDA, 2004, for colorectal cancer.
That's right.
And it was a huge conceptual shift because it attacked the cancer support system, not just the cancer cells directly.
A complete new angle.
A great example is bevacizumab, right? Avastin is the trade name. It cuts off those feeding vessels. And now it's used for colorectal, brain, ovarian, cervical, lung cancers. Quite a range.
It is. It's become a key tool.
But, okay, if these drugs are so good at cutting off supply lines, why don't tumors just find a workaround? Do they adapt once Avastin hits them?
That's a really critical challenge in oncology. Tumors are, well, they're genetically unstable, highly adaptable. So while anti-angiogenic drugs definitely extend survival, they rarely cure the cancer on their own. because over time, some cancer cells mutate. They find ways to survive in that low oxygen environment, maybe using different metabolic pathways.
I see.
But the approach buys precious time. It significantly slows down the cancer's growth rate, making it a vital part of a multi-pronged treatment plan.
Right, it's one piece of the puzzle. Which brings us to the next major breakthrough, and maybe the most transformative one, immunotherapy. So if targeted therapy is like precision missiles, immunotherapy is more like activating the body's own internal defense force.
That's a perfect analogy. That internal defense system is an army of super soldiers. Or think of them like cops on the beat constantly patrolling your body.
Right.
Their natural job, day in and day out, is finding trouble like microscopic cancers and just knocking them out before they even get big enough to need a blood supply. Your body is actually fighting cancer constantly.
Wow. And the potential here is, well, it seems massive. Using immunotherapy to kind of jack up this immune system, physicians are seeing cases where patients with stage 3, even stage 4 cancer, the stage is often seen as historically end stage, game over. They can potentially see tumors shrink down to undetectable levels. It's like turning a late stage diagnosis into something that looks like stage 0.
The breakthrough that allowed this supercharging is a class of drugs called checkpoint inhibitors. Probably the most recognized name is pembrolizumab, sold as Keytruda. See, cancer cells are sneaky. They often wear a sort of molecular cloak to hide from the immune system's surveillance.
An invisibility cloak.
Pretty much. They do this by exploiting natural checkpoints. These are molecular breaks that normally stop the immune system from attacking healthy tissue. Cancer hijacks these breaks.
So the drugs disable the breaks the cancer is using?
Precisely. These drugs work by essentially pulling the cloak off the cancer. By blocking signals like PD-1 or PD-L1 receptors, the drug lets the patient's own T cells, the main attack force of the immune system, finally see the tumor and destroy it. It's a complete game changer. Because we're not adding a poison. We're just telling the immune system, okay, go do your job.
Okay, so for someone listening, what should they know about eligibility? When a tumor biopsy is done, what are the key markers they should be asking their doctor about?
The tumor analysis is absolutely critical for predicting who will respond well. You should definitely ask if the biopsy was tested for markers like MSI, that's microotolite instability. Tumors with high MSI levels tend to be very unstable genetically, and they often respond exceptionally well to these checkpoint inhibitors.
Got it. MSI.
And furthermore, they'll look for the presence of those specific cloaking targets we mentioned, PD-1 and PD-L1, because those are the exact molecules the drugs like Keytruda are designed to interact with.
Right. So we've gone from generalized poison to laser-targeted signaling, and now to activating our own internal army. That's a massive conceptual journey. But here's maybe the most surprising part. This powerful immune army doesn't fight alone. Its success seems to really depend on a partnership it has with the, 39 trillion residents of our gut?
The microbiome.
Gut microbiome, yes. It's foundational for overall health. We know it helps lower inflammation systemically, it aids metabolism, influences mood. But recent research shows it's like a co-pilot for the immune system, especially when that immune system is being kicked into high gear by immunotherapy.
And this is where the findings get really, really interesting. There was a major study back in 2017. Researchers looked at cancer patients getting those checkpoint inhibitors. They wanted to know why some patients were responders, had amazing results, while others were non-responders. Their first guess was maybe genetics or complex lifestyle stuff.
But what they actually found was, well, frankly shocking. So the difference often was simply the presence or absence of specific bacteria in the gut.
The patient's microbial makeup seemed to dictate the success of these incredibly advanced drugs.
And they pinpointed a specific key player, a bacteria called Akkermansia mucinophila.
Yes. And the evidence was compelling because they didn't just see a correlation, they showed causation. The researchers took fecal material containing A. mucinophila from human responders and transplanted it into lab animals that weren't responding to immunotherapy.
Okay.
And after that transplant, the animals suddenly started responding really well to the checkpoint inhibitor treatment.
Incredible.
So if you connect this to the bigger picture, it strongly suggests that success in modern cancer treatment isn't just about the drug. It's also about optimizing the internal environment, the terrain, to help the drug work effectively.
That is such a powerful and actually actionable insight. So for anyone listening, the logical next question is, how do we cultivate this beneficial bacteria? We need to talk about food as fuel for this partnership.
That's exactly right. If we know certain bacteria are critical, we need to feed them what they like. And generally, what beneficial gut bacteria thrive on are two main things: dietary fiber, and polyphenols.
Polyphenols, those are the colorful compounds in plants,
Yeah.
right?
Exactly. Think of them as the brilliant pigments, the protective compounds found in colorful whole plant foods.
So deep colors, lots of fiber, but the research gets even more specific for Akkermansia, pointing to foods rich in compounds called allegitannins. These are like precursors that help it grow.
That's where the specific list comes from. You can find allegitannins in foods like pomegranates, dried cranberries, Concord grape juice.
Okay.
Beyond that, just general high-fiber foods that act as prebiotics are key. Things like oats, oatmeal, whole grains generally. And surprisingly, even things like dried chili peppers, chili flakes, and Chinese black vinegar, the kind you get with soup dumplings, they also contain compounds that seem to stimulate this beneficial bug.
This isn't just about eating healthy in a vague sense. It connects directly to clinical outcomes. There's a specific, really memorable fact about fiber you should hold on to. One study showed that for every 5 to 6 grams of dietary fiber someone added to their diet, that's about the amount in one medium-sized pear.
Just one pear's worth.
Melanoma patients who were receiving immunotherapy had a staggering 30% reduced risk of mortality.
30%. That number should really make everyone pause. It highlights that the body's own health defenses aren't just some side benefit to treatment. They are integral to the treatment's success. This totally reframes the conversation. It's not about food versus medicine. It's profoundly about food and medicine. Diet strengthens those foundational systems. It lowers inflammation, boosts the microbiome, and that, in turn, amplifies how well these cutting-edge drugs work.
So what does this all mean when you put it together? The fight against cancer today looks like an integrated multi-system strategy. It combines surgery, plus targeted therapy like anti-angiogenesis to starve the tumor, plus immunotherapy to unleash the body's internal army, all of it anchored and amplified by these crucial foundations: a healthy diet and a robust microbiome.
And the key takeaway for you, the listener, has to be the need for self-advocacy. If you or someone you love is facing cancer, you need to feel empowered to ask your oncology team specific questions. Ask them, beyond the standard treatments, am I eligible for anti-angiogenic therapy or other targeted treatments based on my tumor's specific genetics?
Right.
And critically, has my tumor been sent for analysis to check for those key markers like MSI, PD-1, or PD-L1? These tell us about my likely response to immunotherapy.
Knowing those markers can genuinely change the entire path of care. And remember, this field moves incredibly fast. A great resource if you're looking beyond standard options is clinicaltrials.gov. You can actually go there, type in your specific cancer, your interest in targeted therapy or immunotherapy, and see what clinical trials might be available and enrolling right now.
That integrated, informed approach really is the new standard of care we should all be striving for.
So here's a final thought to leave you with. If simple dietary choices like adding the fiber from just one pear a day can drastically boost the power of our most advanced cancer drugs, what other basic everyday habits might be secretly influencing the success of complex medical treatments across all sorts of different diseases? Something to think about as you optimize your own internal environment.